This section starts out with a topic that we're pretty familiar with. It's separation of variables. So we have dy dx is equal to x squared y squared, 1 over y squared. Dy is x squared dx. And then we integrate, so that's negative 1 over y is equal to 1/3 x to the third plus c. So negative 1 over 1 is 1/3 times 1 to the third plus c. So we have a negative 1 is equal to 1/3 plus c. So c is negative 4/3. We have negative 1 over y is equal to x to the third over 3 minus 4/3. So 1 over y is 4/3 minus x to the third over 3. And then these two are going to trade places. We got y is equal to 1 over 4/3 minus x to the third over 3. And then we're going to multiply the top and bottom by 3. We get 3 over 4 minus x to the third. Here we have law of exponential change. You have probably solved enough exponential growth problems by now to recognize that they involve growth in which the rate of change is proportional to the amount present. So the growth in which the rate of change is proportional to the amount present tells us that this is exponential growth. Now here is the growth right there, a rate of change. And it's proportional. There's the constant of proportionality, and there is the amount present. For example, if you have more money in the bank, your bank account is going to grow faster than if you had less money in the bank. Here we separate the variables, divide by y, integrate both sides. So we have natural log of y, and the integral of k is kt. Change to exponential form. This is e to the kt times e to the c. And we just write e to the c is just c. So this is exponential growth, and it comes from the fact that the rate of growth is proportional to the amount present. Now we've seen that as the PERT formula. So in money, the amount in the bank account is the principal times e to the rt. In like bacteria and science, they say n is n naught e to the kt. Here we have continuously compounded interest, but it actually starts out with compound interest. So let's look at this very quickly. This says that the amount in the bank is the principal. Let's say you had $800 in the bank. And you get all of that $800. So you get 100% of it plus, if you had, let's say, a 3% annual percentage rate, and you're going to compound that 12 times a year or once a month. Well, you only get a 1/12 of that rate per month. You don't get 3% every month. So at the end of the year, you get 12 times a 1/12 of 3%, which in the end ends up being 3%. So we're going to take that 3% and we're going to divide by 12, but you get that 12 times. And then how many times a year do you get that? Or how many years will you get that interest? 1 year, 2 years, 3 years? So hopefully that takes out the mystery in this a little bit at least. The amount of money in the account after t years is P equals e to the RT if we compound continuously. So continuous interest rate is the PERT formula. So let's try these two problems. I've worked out the decimal answers, and I assume you can actually punch this into your calculator and get a correct answer. So we're just going to write the answers. So letter A, suppose you deposit $800 in an account that pays 6.3% annual interest. How much will you have 8 years later if the interest is compounded continuously and compounded quarterly? So let's look at A, continuously. The amount is going to be 800 e to the 0.063 times 8 years. And when we put that in the calculator, we get $1,324.26. For compounded quarterly, the amount, I guess I should have had amount, not P here, amount in the bank, is the principal times 1 plus, actually, we know the principal. I'll get it. Let's see. 800, 1 plus 0.063 divided by 4 because it's quarterly, but you get that 4 times a year, and then we're going to do that for 8 years. So in the end, you get $1,319.07. At the beginning of the summer, the population of a hive of bald-faced hornets, which are actually wasps, is growing at a rate proportional to the population. Growing at a rate proportional to the population tells us that this is exponential growth. From a population of 10 on May 1, well, let's write a few things. So the number of wasps is the initial amount, e to the kt. And they tell us that on May 1st, we have 10. So at the initial value, the initial date is May 1st. The number of hornets grows to 50 in 30 days. So in 30 days, we have 50. If the growth of the population continues to follow the same model, how many days after May 1st will the population reach 100? So how many days will it take for the population to reach 100? Well, we know the initial population. We know that's 10, e to the kt. Well, now this tells us and not. This allows us to find the k. So 50 is equal to 10 e to the k times 30. So we divide by 10, take the natural log of both sides, and divide by 30. So that is, let's see, I have the decimal for that somewhere, 0.053. But we're going to use the value that's sitting in the calculator. We're not going to actually use this rounded answer. We're just going to write that one down to represent what is in the calculator. So n is equal to 10 e to the 0.053t. Well, now we can plug 100 in for n, 10 e to the negative 0.053t, divide by 10, take the natural log of both sides, and t is equal to 42.920 days. Scientists who use carbon-14 dating use 5,700 years for its half-life. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. All right, so we have the amount is equal to the initial amount, e to the kt. It says it takes 5,700 years to reach half-life. So we'll have half of the initial value in 5,700 days, or years actually. Well, we can divide both sides by n naught, so here's what we're left with. Take the natural log of both sides. So k is natural log of 1/2 over 5,700. And that is negative 0.0001. Now, there's more numbers in the calculator. There's more, but we're going to represent the number with that right there. We have n is equal to n naught e to the negative 0.0001t, because that's the k. Well, now we want to know when 10% has decayed. So in other words, when we have 90% of the original amount. So we have 0.9 is equal to e to the negative 0.0001t. We'll take the natural log of both sides. So t is equal to 866.417 years. Hard-boiled egg at 98 degrees Celsius. So 98 is the original temperature. Is put in a pan under running 18 degrees Celsius water. That's the surrounding temperature. We're surrounding the egg with that temperature. After 5 minutes, the egg's temperature is found to be 38 degrees. So after 5 minutes, the temperature is 38 degrees. How much longer will it take the egg to reach 20? So we'll find out how long it takes, and then we'll subtract 5, and that's how much longer it takes. So this is to find the k. Now here's the formula over here, and we're not asking you to memorize that. We'll give you that formula. So 38 minus 18 is equal to 98 minus 18, e to the negative k times 5. So I used this point in the formula here, and all we have left is k. 20 is equal to 80 e to the negative 5k. 1/4 is equal to e to the negative 5k. So the natural log of 1/4 is equal to negative 5k. So k is equal to, I have that all worked out somewhere. That k is 0.277. Well, now we can plug this point in with the k plugged in also. 38 minus, no, not 38. We want this to be 20. 20 minus 18 is equal to 98 minus 18, e to the negative 0.277 times t. That's what we're trying to find the time. 2 is equal to 80, e to the negative 0.277 t. We'll divide by 80, e to the negative 0.277 t. Natural log of both sides, negative 0.277 t, and divide. So t is equal to, ends up being 13.304. So that's what would go here. But to answer the question, how much longer, we'll subtract 5 from that, and that's going to be 8.304 minutes. Here we have separation of variables. That's going to be 1/2 y squared is negative 1/2 x squared plus c. Y is 3, so 9/2. I should show that I'm using this. 3 squared over 2 is equal to negative 4 squared over 2 plus c. So we have 9/2 plus 16/2 is 25/2. So we have 1/2 y squared is equal to negative 1/2 x squared plus 25/2. Let's multiply everything by 2. That's 25 minus x squared. And then we want positive 25 minus x squared, this positive square root, because y is positive. That's the top half of the circle. If that would have been negative 3, we would put a negative out in front of the radical because that would be the bottom half of the circle. Here we have 1 over y dy is equal to 2x dx. So we integrate. Natural log absolute value of y is x squared plus c. Natural log of 3 is equal to 0 squared plus c. So c is natural log of 3. We have natural log absolute value of y is x squared plus natural log of 3. So y is equal to e to the x squared plus natural log of 3, and I would make that 3e to the x squared. Find the solution of the differential equation. This is exponential growth. So we can just go right to y is equal to y naught e to the kt. Well, they give us the initial value, so we know that's 200, and they even give us the k. That's negative 0.5 t. One isotope of Neptune has a half-life of 65 minutes. If the decay of Neptune 240 is modeled by the differential equation where t is measured in minutes, what is the decay constant k? So half-life is 65 minutes. Well, k with half-life is natural log of 1/2 over 65. Do I have that value? Let's see. 0.01066. Keep on going. Colony of bacteria is growing under ideal conditions. I'm going to move this for later. So like next year, I'll have a little bit of room down below. A colony of bacteria is growing under ideal conditions in a laboratory so that the population increases exponentially with time. So population increases exponentially with time. So it's exponential growth. At the end of 3 hours, there are 10,000. And at the end of 5 hours, there are 40,000. How many bacteria were present initially? So N naught is equal to what? Well, we have n equals n naught e to the kt. So let's fill in for both. Let's fill the values in for both points. So n naught e to the k times 3, and 40,000 is equal to n naught e to the k times 5. Well, we can divide equations. We can divide equations when we have a system of equations. And I actually want to divide this way. So 40,000 divided by 10,000 is 4. The n naughts cancel out when we divide, and we always subtract the powers when we divide. So the natural log of 4 is equal to 2k. So k is equal to natural log of 4 over 2, which is, when we do that in our calculator, 0.693. 0.693. I'm going to use the whole number in the calculator, but we'll represent it with 0.693. I got to plug that back in somewhere. So let's do this one. 10,000 is equal to n naught e to the 0.693 times 3. So now that's n naught times this number. So we just have to divide that over. So when we do the division on the calculator, it ends up being 1,250. Now it didn't matter if I picked this one or I picked this one, we would get the exact same answer. An aluminum beam was brought from the outside cold into a machine shop where the temperature was held at 65 degrees Celsius. So the surrounding temperature is 65. After 10 minutes, the beam warmed to 35 degrees. That allows us to find the K. And after another 10 minutes, its temperature was 50. Use Newton's law of cooling to estimate the beam's initial temperature. So we want T naught. All right, well, if we have 35 minus 65, that's equal to T naught minus 65 e to the negative k times, what's the t? The t is 10. Jeez, took me way too long to find that. Negative 30 is equal to T naught minus 65 e to the negative 10k. Well, how about the other one? How about the other point? We have 50 minus 65 is equal to T naught minus the surrounding is still 65, e to the negative k times 20. So that's negative 15 is equal to, actually, let's put it over here. Negative 15 is equal to T naught minus 65, e to the negative 20k. So let's divide these. And we'll divide top minus bottom because that'll be 2. Those cancel. And negative 10 minus negative 20 is positive 10. So e to the 10k. So natural log of 2 is equal to 10k. So k is natural log of 2 over 10. Did I have the decimal value for that. That's is equal to where is it? Let me look here. 0.069. Well, now we have to use one of these to finish out the problem. How about this one right here? Let's take that one. And that's going to be negative 30 is equal to T naught minus 65 and then e to the negative 0.069 times 10. Well, let's divide by this right here, and then we just add 65. So T naught ends up being 5.